Find integers that are upper and lower bounds for the real zeros of the polynomial x to the fourth minus 2x cubed plus x squared minus 9x plus 2. The first step we want to do is to find the possible rational real zeros of the polynomials using the rational zero theorem. The possible real zeros are of the form p over q, where p is a factor of the constant coefficient of the polynomial. The constant coefficient is 2, which has a factor of plus or minus 1 or plus or minus 2. Q is a factor of the leading coefficient. The leading coefficient is 1 in this case, the coefficient of the term with the highest degree. And so Q can only be plus or minus 1. If we take any number P divided by Q, then the possible zeros are plus or minus 1 and plus or minus 2 only. Next, we pick a number on that list and perform synthetic division to check to see if it is indeed a 0. K is 1. The coefficients of the polynomial, starting with the coefficient of the highest degree term, which is 1, and then negative 2, 1, negative 9, 2. Remember that if there is any missing terms, we would have to put 0 in there. In this case, all of the terms are present: x4, x cubed, x squared, x, and then constant. To perform synthetic division, we bring down the leading coefficient and we multiply k. 1 times 1 is 1, and then we add the number in that column. Negative 2 plus 1 is negative 1. And then repeat. Negative 1 times 1 is negative 1. 1 plus negative 1 is 0. 0 times 1 is 0. Negative 9 plus 0 is negative 9. Negative 9 times 1 is negative 9. And 2 plus negative 9 is negative 7. Now, because the remainder is not 0, we know that x equals 1 is not a 0. The last entry in the synthetic division has negative, but the sign is not alternating between non-positive and non-negative because of the last two numbers. And so this synthetic division doesn't reveal anything about the upper and the lower bounds of the zero. And so we need to move on to x equals negative 1. Bring down 1. 1 times negative 1 is negative 1. And then negative 1 plus negative 2 is negative 3. Negative 3 times negative 1 is positive 3. 1 plus 3 is 4. 4 times negative 1 is negative 4. Negative 4 plus negative 9 is negative 13. Negative 13 times negative 1 is positive 13. And then 2 plus 13 is 15. We notice that, sure, x equals negative 1 is not a 0 because the remainder is not 0. But in this case, the entries in the last row alternate in signs. Positive to negative, negative to positive, positive to negative, negative to positive. This means the entries are alternating from non-positive to non-negative. In this case, x equals negative 1 is a lower bound of the 0. Unfortunately, it is not a 0, but at least we know now that if there is any 0, it has to be on the right-hand side of negative 1, which might be useful in many cases. In this case, not so much, but at least we know that we do not need to check x equals -2 to see if it is a 0, because again, x equals -1 is already a lower bound for any possible zeros. There is no 0 on the left hand side of -1, so we do not need to check x equals -1. And so what left is x equal 2. We will now check to see if x equal 2 is a 0. Again, we do not need to check x equals -2 because -2 is less than -1, and -1 is already a lower bound. Perform synthetic division on k equals 2. We bring down 1. 1 times 2 is 2. -2 plus 2 is 0. 0 times 2 is 0. 1 plus 0 is 1. 1 times 2 is 2. -9 plus 2 is -7. -7 times 2 is -14. 2 plus -14 is -12. Since the remainder is not 0, x equal 2 is not a 0 of the polynomial. We check x equals 1. We check x equals -1. We don't have to check x equals -2. And we should check x equal 2. None of these is a 0 of the polynomial, but the synthetic division only check if the rational real zeros of the functions exist. There might be irrational zeros of the function, but synthetic division cannot check those. Now the question asks us to find the upper and the lower bounds for the real zeros. We found the lower bound already. We haven't found the upper bound yet. Even though x equals 3 is not a 0, but since we check x equals 2 and the last entry doesn't reveal anything to us, we now check the next integer, which is x equals 3. We perform synthetic division on x minus 3 as the divisor. And again, we know that x equals 3 is not a 0, but what we're doing here is to check the upper bound for the zeros. We bring down 1. 1 times 3 is 3. -2 plus 3 is 1. 1 times 3 is 3. 1 plus 3 is 4. 4 times 3 is 12. -9 plus 12 is 3. 3 times 3 is 9. 2 plus 9 is 11. Now, the last entries, the last row does not have any negative number. What that means is that x equals 3 is an upper bound for the zeros. And so if there are any zeros, they have to be between -1 and 3 only.